continue what we have been doing. So therefore, in the first two talks, we have been introducing several elementary models for either for general image processing and especially for image segmentation. We talk about the Mumford-Shah, piecewise constant Mumford-Shah, geodesic active contour, and then we introduce a level set. So I think last lecture we introduced level set. So yeah, so I think today we continue. So we continue with piecewise constant levels, and we skip this one, and then talk about convex relaxation. Especially these things are very new, and so we hope you see today, tomorrow we can go through most of it. Maybe this part we can try a little bit in the later. And these methods are normally very, very fast and very stable. So those are, if you use it for segmentation and number of applications, really it's very good. Yeah, so here are the elementary models. So therefore we talk about for image segmentation, essentially it must be either region-based or edge-based. And the first variational method was a snake model. You see this is essentially use elasticos and plus an edge detector to detect the edges from an image. And then we talk about Mumford-Shah. And so here is a Mumford-Shah. And piecewise constant Mumford-Shah. Even the simplicity case is two constants. So this you can use as a background, foreground. A more general case, and we relate this to the pulse model. Here is a geodesic active contour. So you just use the edge detector from the edge. So how do you combine elasticos we talked about earlier? So the numerical techniques, essentially last lecture we go through the Levelset methods. So compare, because the snake models are normally so easy. You have some weak points. So we talk about the level set. Especially we talk about the Convex, so who is using the Levelset method for the two-phase piecewise constant Mumford-Shah. I think here is the essentially you see the original piecewise constant Mumford-Shah. You need to find two regions such that those two regions has no overlap, no vacuum. And then the boundary is the interface is gamma. You minimize the gamma C1, C2 such that this functional is minimized. So this is a two. So both C1, C2 are unknown. Also gamma is unknown. So this is C1, C2 is easy to solve, but solving gamma is a difficult problem. So therefore, you see the crucial contribution of the Convex model is that you don't solve this gamma, so you replace it by Levelset function, such that this gamma is a zero Levelset function. This must be closed curve, so therefore phi inside is positive, outside negative. So therefore, if you replace by heavyset phi, you see this term heavyset exactly equal to that one. So 1 matter heavyset exactly equal to this one. And the length is the total variation. So this is a crucial point. So you don't move the curve anymore. By just such a simple replacement, the original is a very difficult minimization with the gamma, and then you replace by easy minimization with phi C1, C2. So therefore, you see, it's this function is easy to minimize with phi as well. So you mostly in numerical simulation, you smooth the heavy set, and do find out what's the Euler-Lagrangian. So you smooth the heavy set. So here is the C1, C2 is easy to calculate. So I have corrected the tuples. So the variation with the phi is also this term is a little bit tricky, but you easily get the Euler-Lagrangian equation. I have corrected the tuple from the last lecture. And so therefore you see that to really solve the two-phase Levelset function is essentially you use gradient descent to minimize with the phi. And then you see C1, C2 is a quadratic, you just minimize it exactly. Quadratic minimization, you can get exact minimizer. So here mostly you just use a time descent. At the time t, you go in the negative direction of the gradient. So in numerical simulations, you smooth, this is a delta function, is a derivative of a heavyset function. You smooth this one, also you smooth here. Because if the gradient is equal to 0, you get trouble. So this is you use a gradient descent to move the level set. And mostly you use explicit formula. You see number of iterations, and then you update C1, C2. If you do alternating between those two, you solve the Convex model. I think this is mostly people use. This is the original numerical methods which was proposed in the Convex paper. If you use more regions, and then you need to use more level set. Using 2 level set, and then you can segment the region into 4 regions. You see, in one region equal to C1, C2, C3, C4. So therefore, you get a function which is piecewise constant with 4 constants. In this case, you see the multi-phase Convex model. Essentially, you see that you want to segment a region into 4 regions. You see, each region have one constant. You see, each region have a constant, so therefore essentially, so the in 4 phases, so you minimize, so and then you can have 4 regions. So omega 1, so here is U0 minus C1, and then here will be omega 2, U0 minus C2, and then omega 3, omega 4. So this will be, you see, you segment into 4 regions. Each region you approximate constant, and then here you regularize the length. You see that mostly you want to regularize the length of the interfaces. So this will be the. So this will be the original one, piecewise constant Mumford-Shah. If you want to segment into 4 phases, you see each phase approximate 1 constant, you want to regularize the length. And so this is still difficult to solve due to you need to move the interface of the omega i's. So therefore, what the Convex set does is still introduce 2 level set functions. You see phi 1, phi 2 as in the previous page. So phi 1, phi 2 is you have a 2 level set functions according where is a positive, where is a negative, and where is a zero. And so here is using level set for the 4 phases. So essentially you see that heavy set, and this is only non-zero in one region. This is the non-zero another region. This is non-zero another region. Non-zero another region. So therefore, essentially, you see this reduces maybe omega 1, omega 2, omega 3, omega 4. So those become those 4 terms. You turn it into a minimization with phi. But the minimization of this one is, you see here, if you use the original Mumford-Shah, so you want to minimize the length of all the interfaces. The length of all the interfaces. So therefore, you see that here, essentially, you see that this is a total variation of each phi 1. This is a total variation of phi 2. So those are, these are the lengths of this region plus the length of this one. So it's the length of this boundary plus the length of this boundary. So with this figure, you see this length exactly equal to this one. You see, if the boundary is, if the face is like this one, those two are exactly the same. But there are cases, so this is not the same. This is not the same. Especially, I think you see that. I think you see, if you have especially have a 3-phase, if one of the phases is empty, assuming you see that. So on this side. On this side, the phi 1 is positive. On this side is phi 2 is positive. And then this length is counted twice. And those 2 lengths are just counted once. So in such a case, you see this one does not equal to that one. So therefore, there is a little bit difference from the original the piecewise constant Mumford-Shah. So in this figure, those 2 exactly equal. So the sum of those 2 total variations, equal to the length of the interface. But if such a thing happens, So you see one of the lens is counted twice, the other lens counted once. But also there are even four phases. It can happen, you see, some of the edges are counted twice, some of the edges are counted once. So therefore you see that this regularization is not exactly the lens regularization, right? And so there's, yeah?
Each interface must have a same alpha, or you can put a...
You can put a different alpha. So therefore that... so I think you see that even you see this one. So, okay. So therefore you see this essentially you can write, you see, like a minimize omega I ci from 1 to 4. So here is a sum. So here is omega I u0 minus ci squared plus alpha of the length of yeah. So here the original one will be the length of omega I. So so this is the original piecewise constant one for sure. So the Convex is essentially you minimize phi 1 and phi 2 and ci I from 1 to 4. So here is a sum. Here how do you write? Let's see. Okay, we see this is a characteristic function of the region, which depends on phi 1, phi 2. So here is a u0 minus ci. Here is a plus alpha. So here is the total variation of phi 1 plus the total variation of phi 2. So your question that can this alpha be different on the different interfaces? So in fact, so yesterday or in the last lecture we talked about, you see this equal to the length. But you see that you can really use a geodesic here. Instead of equal to the length, you can really put an edge detector even. So you get a G. Maybe here is a smooth U, and then here you get phi 1 and phi 2. So here, instead of taking a constant, you can add an edge detector. So if your edge detector, this is not a constant. It differs from every point to point. So therefore, this edge detector, normally you take a 1 plus a C gradient. This is a smooth mode of U0. If you do this one, you see that this is, so the original Convex, you just put the length, put the constant, that regularize the length. But in the new method, you can just put the edge detector. So in this case, you see that it's not constant, it's a weighted length. It's a weighted length. So here is essentially the corresponding characteristic functions. So there's no need to just take a constant here. You can take anything, even if you put on an edge detector, so that makes things much, much better. I don't know, you see, this idea is known to many people, but still you see that due to the traditional people normally still just take a constant. Just take an edge detector would be very good. So this will be the multi-phase, and then you get the Lagrange equation for phi 1, phi 2, and do gradient descent. Still, you see like C1, C2, C3, C4 is a quadratic, especially if you take a beta equal to 2 is a quadratic. So that will be very easy to minimize. So this will be the multi-phase Convex. And the advantage is that really use Levelset. It can handle very complicated geometries. It's region-based, so it's very robust with noise. You can have an image without edges. So if you have some image, so here is darker, here is brighter, but there's a slow transition from a dark region to the blue region, and then the whole image there is no edge. If there is no edge, you can still use a region-based method to segment, but if you use edge-based method, you cannot. But however, you see that if you put here edge detector, and then it will be as good as edge-based methods. So it will combine both methods together. So here will be the region-based, here will be edge-based. So these will be the two phases, two level sets. If you use more level set, then you get more regions. The disadvantage is that mostly people use, you see, like iterative method to evolve the level set. So you can see clearly how the level sets are moving around. But that also gives a slow convergence. Mostly you see you have a 3D data, you push the button, you want to get the result. So if you move slowly, so that gives a slow convergence. Another one is due to its non-convex minimization, so it gets stuck with a local minimizer and depends on initial values. So you see, like here, you start with this curve, you segment this, the cameraman out. You start with this curve and you segment only the upper part. This becomes, so that's due to the non-convexity. You get different minimizers. You get stuck with a different minimizer. So the levels that you see, like a snake model, is essentially trying to move the curve. So the level set is that it is moving the curve, but it does directly move the curve and move the function up and down. So the corresponding zero level set curves are moving. So you see, so we can see that the philosophy are different. So snake model directly move the curve. You put many points on the curve, you move the points, and then the curve are moving. Level set, you don't directly move the curve. So I move the level set function up and down. Because the level set function is moving, so the corresponding curve is moving. Here, recently, there is another philosophy that you don't move the curve, also you don't move the level set function, you do a labeling. So we call it piecewise constant level set, and the labeling function is essentially like this one. So if you want to partition this region into three regions, like 1, 2, 3, 3 regions, and then how do you identify the region? Each region I give you a label. Assuming you see, I know I want to identify to 3 regions, and then each point I only give you 3 labels. In the beginning, you don't know, you see, which label is correct, but then you need to reshuffle the label. And once the label is shuffled correct, the integer will be minimized. If the label is not correct, it will not be minimized. So if we want to identify the region to n region, we give n labels. And labels. And this is where you see, the philosophy is again is different. The snake model directly moves the curve. The level set doesn't move the curve. You move a function up and down, and then the corresponding curve moves. So the labeling is again another philosophy. So I don't move the curve at all. So just each point, I need to have a label. If the label is correct, and even Kim was talking about something very related. So the label is correct, and then the integer will be minimized. And so this is, again, is another philosophy. And there are different ways to label it. So assuming you know there's n labels, if you want to avoid vacuum and overlap, so you ask this polynomial, this is polynomial of order n, you ask this polynomial equal to 0 everywhere. If this polynomial is equal to 0 everywhere, and then the label must be one of the n labels. So there will be no overlap, no vacuum. If this is equal to 0, you see phi must be one of those labels. It cannot be anything else. That gives you a unique labeling of the pixels. And then once the label is known, the corresponding characteristic function of the regions are known. So here, if you multiply all those things together, it will be equal to 0, right? If you just pick one of them out, and then this function will be 0 everywhere in every other labels, but only in the region of the ith label is not 0. You scale it by the same constant, so this function will be equal to 1 omega I 0. So these were the corresponding characteristic function, right? So therefore you have the label, and then you have the characteristic functions. If you have the characteristic function, and then And then you see that once you have the characteristic function, all the geometrical information of the region of the boundary can be calculated the characteristic function. So if you have a region, if you know the characteristic function phi equal to I here, if you know the characteristic, you know how to calculate the area, you know how to calculate the length of the boundary, you know how to calculate the curvature, you know how to calculate the normals. So once you know the characteristic function, you know everything about that region, and then you can turn, you see, all the geometrical minimization things into the characteristic function, and then again into the phi function. Yeah. So there, if you do this one, so how do you see, this is, we repeat that this is the piecewise constant bound for SHA. So you need to partition into omega I region, each one into Ci. This has no overlap, no vacuum. So here you regularize the length. And the geodesic, so we'll repeat a little. So the geodesic is you have edge detection. So this function, you smooth the image, and this function is small at the edge. You want to find the curve such that integration of this function is small. So the global minimizer for such a functional is always a 0. If this curve is empty, and this will be 0, that's a global minimizer. That's a weak point. But otherwise, you see this curve, if you start with a curve which is you see, surrounding the edge points, and then it will shrunk. Once this curve getting into the edge, and then will stop there, because the integration of this one on such a curve is the smallest. If you shrunk even more, so this is getting bigger. So this is essentially is like this. That was I should have right. This is edge detector. So you have a function, and this function is the smallest here. You want to find the curve such that integration of this function on that curve is smallest. So the empty curve is a global minimizer. But assuming you start from a big curve surround this one, and then the curve shrunk, and suddenly the curve is getting to here, and then it cannot shrunk anymore. Because if you shrunk, the curve will come to here, and then the energy will be increased. So this is a geodesic additive contour model. So this is a geodesic active contour model. So here is the edge detector. On the edge, this is very small. And mostly you try to find a curve such that this integration curve of this function here. You see, for that edge detector, if you start with a big curve and shrunk to the circle, and then this curve cannot continue anymore. So this is the geodesic additive contour. Well, exactly, that's what your question. So can you take a constant? So therefore, instead you can combine the region-based omega 1 here, and you put the edge detector. So these will combine both. These will come in both. If this take a constant and reduces to the Convex model, to the Convex. But if you don't do that one, so this will combine the advantage of both. And so therefore, you see, if you use a piecewise constant level set function, how do you solve it? So how do you solve it? So again, you can do such a transformation. So here is omega I. So here is a boundary for omega I. So you can still do such a transformation. So if you put on the characteristic function here, integration on the whole omega, this will reduce to omega I. Here I read the u function. So the u function is equal to Ci multiplied with the characteristic function. So this u function is equal to Ci in omega I, right? This u equal to Ci in omega I. So u, if you write in that way, so u equal to Ci in omega I. So therefore, you see here, psi I equal to 1. So here reduce omega I. So this u to Ci. So exactly this term reduces to this term. Exactly reduce it to this term. And then here you need to use a covariance formula. If you use a covariance formula here, if you put the total variation of the function, and that's equivalent to integrate on the boundary over here. So use a covariance formula. So this term will reduce equal to d omega I g gradient u sigma ds. So that term reduces to here. And so therefore you see those two, so exactly those two terms equal to those two terms. So again, original minimization with Ci, now you become a minimization of phi. So this u depends on phi in this way. This depends on phi. This does not depend on phi. This depends on phi. But then you need to have such a constraints to avoid the overlap of vacuum. To avoid overlap of vacuum. So if you do this one, so therefore the previous model, the previous piecewise constant first shot model, and combined with the geodesic advent contour, become a minimization of this one. Minimization of this one. So this is another way to transform the problem. The Convex model uses a level set to transform the minimization with the interface into a level set function. And here we can use this way to transform the minimization with the labels in such a way. So very often you see this produce exactly this term. But however, you see, you can simplify it. You can simplify, just replace it by this one. If you do this one, because phi is not 0, 1, and the jump of phi comes in. So phi sometimes jump from 1 to 2, sometimes jump to 1 to 5. If here jump to 1 to 5, so the length will be multiplied by the jump. So that's the only thing. But if you do this one, a lot of things will be simplified. So this is a simplified version. And then you can solve this one under this constraint. And so this is another way to solve it. So
do you use this term as the function or not function?
Here. Yeah. Mostly this will simplify the computation quite a lot, because if you use this one, you can still calculate your Lagrangian, but the term is rather complicated. I will show in the next slides. Using this one, you see, make it much easier. But then you see here the jump of the function comes in, and that's mostly not a problem. So you can see that, and so therefore this is another philosophy. You don't move the curve. I just want to identify the label. If the label is correct, and then this integer will be minimized. So it's another philosophy. This is like you go to the cinema, right? Assuming you see the Keister go to the cinema, Yonsai also go to the cinema. Keister will be all sitting on the left, another one will be sitting in the middle, another one will be sitting in the right. So if you don't sit in the correct seat, you don't find your neighbor knows about you, so you don't talk with him. Maybe the noise is very low. If you want to maximize the noise, most probably you must sit in the correct one. So each one must have a correct seat. And this is again, if the seat is correct, this will be minimized, and that will be satisfied. So this is another idea. So the essential problem is this constraint. How do you deal with this constraint? So here you see we are trying to use like a continuous minimization approach. Even this phi can only take a finite number of values, but we think that phi can take any value. And then we impose this constraint. As a Lagrange. Here is a penalization. Here Lagrange use those two techniques to guarantee that in the end, the k phi equal to 0 will be satisfied. So this is essentially regarded as, so this minimization problem is a discretized minimization problem. So your minimization does not have a continuous value. You only have a finite number of discretized values. But if you do this one, we are essentially regarding a discretized minimization problem as a continuous minimization problem and solve it. When this constraint is satisfied, you only have a discretized value. So in somehow we are making a detour. We are making a detour. But in fact, this problem is a combinatorial minimization. So that's it belongs to the discretized mass. But because we are continuous mass people, so we always transfer into continuous minimization. So the next thing we are going to use, that will be, we really use the discretized. So this is, you have seen this image earlier. So input this one and start with arbitrary. So this is continuous. So start with any initial value. So the label can take anything, not only integer values. But you minimize, in the end it will take integer values and also minimize the image. And this is a segmented image. This is a segmented image. People has been using for many other inverse problems, like estimate the permeability. So here is a reservoir. The reservoir, you want to identify where you have a high permeability, where you have low permeability. In this one, the reservoir has a channel. So they want to identify the channel. So essentially phi equal to 1 here, phi equal to 2 here. You can identify the channels. Also, people has been using this idea for structural minimization, even for electronic devices. So they try to minimize the structure. Instead of using level set, they use a labeling technique. Phi equal to 1, and this is optimal structure. So this is several people from Hong Kong, from different places. They have been using this idea. Yeah. So here is related to your question. So if you really want to exactly minimize the length, so if you don't replace this by gradient phi, if you really want to minimize exact length, so this term, assuming you put everything, this is not related to the derivative, you put everything to here. I'm just trying to show that if you want to minimize the exact length, so what you will get. And then here is the term related to the Euler-Lagrangian. So you have this one, you have the derivative inside, derivative outside. So this is much more complicated PDE. So what we do essentially, we just put one here. So that simplified things quite a lot. If you want to minimize exact length, you need to solve this one. Right. And phase field, I think, I'm thinking maybe let's skip the phase field. If it's necessary, we can come back later. Yeah. So now we go to the convex relaxation. So this is another approach. It's a still labeling approach, but this is another way to do it. So the essential idea is that you see, like a previous approach, the previous approach, we first try to get the labels, and from the label we get the characteristic functions. And then the characteristic functions are related to the labels. And the good point for that one is just one function is enough to identify arbitrary number of phases. And you need one function is enough. But here you see, instead of identify the labels, you can directly identify the characteristics. So assuming you have I have n functions. Each function can only take a 0, 1 at every point. So each function, you have x is from this region omega. You have n functions. Each function can only take a 0 or 1. If you impose this condition, so uix, sum of uix equal to 1 at every point in the region, what kind of ui function you will get? Because each function, so here it should be I from 1 to n. Here it should be I from 1 to n. So each function can only be 0 or 1. And the sum to 1, so there's only one of them is a 1, and everyone else is 0. So that means if those two conditions are satisfied, So each ui is a characteristic function of a region. Right. So there will be no overlap, there will be no vacuum, if those two conditions are satisfied. If this is the case, and then each ui will be the characteristic function of some region. And due to this condition, so there is no overlap, there is no vacuum. In this way, if you want to identify n regions, and then you need to identify n characteristic functions. You need to identify n characteristic functions. Yeah. So this is another approach. It's a label, but this you don't directly label the points, but you try to label the regions using characteristics. If those two conditions are satisfied, each of them must be characteristic. So that's another approach. So if you do this one, and so therefore now we think about the post model. Post model, the Mumford-Shah model, piecewise constant Mumford-Shah model. If the Ci is unknown, if you take Fi equal to Ci minus U0 square, it reduces it to the post model. So let's consider post model. So you have a Fi are given. So this n is given. You have n function are given. You integrate all Fi over omega I. So this should be minimized plus you minimize the length. Definitely here you can put the edge detectors. Let's don't put it. Let's just follow the original post model. And so here is no vacuum. Here is no overlap, and so together. If you do this one, so you can transform this minimization into minimization of a characteristic function such that ui takes the value, each point in the region take the value is 0 or 1. And then you require the sum equal to 1. So therefore the ui will be the characteristic function of omega I. And then you just put the ui here and then integrate in the whole region, and this will reduce to the integration of omega I. Again, you take a total variation, and this will equal twice of that one, because each interface will be counted twice. So this exactly equal twice of that one, but we just use the same lambda. Lambda, you see that, yeah. So in this case, you turn the post model into a minimization of this one. So UIFI here is a total variation. You have this linear constraint. Such that this UI must be characteristic for some region. And this is one transformation. One transformation. So now we are not finding the labels. We are trying to find the characteristic functions. And the thing is that for this model, you can see this term is linear with UI. And this term is convex. The TV is convex. So this whole thing is convex with the UI. And this linear constraint is also convex. So the only thing which is not convex, this constraint is not convex. This constraint is not convex. So what you can do is that so you replace this non-convex constraint, which u should equal to 0, 1, by such an interval. And this will be convex. So you replace it. So here is original ui can only take 0 or 1. But now I instead ask ui to be in this interval. And then this whole minimization problem will be a convex minimization problem. So here is a convex, linear is convex, this is a convex, linear is convex. And this will be a convex problem. The post model is definitely non-convex. When you minimize with the omega i's, that's a non-convex problem. But if you do this one, it becomes a convex problem. And this problem has a global minimizer. We don't know if it's unique or not. You're guaranteed if you start anywhere, if you iterate, you'll get one of the global minimizers. But the non-convex one, you don't know where you end up. So this, you are sure you will go to the global minimizer. And then one crucial question comes out. So here is the the non-convex pulse model. We call it P. Non-convex is due to here. Here is a convex pulse model. One natural question asked, you see that if I solve P, is it equivalent to solve the, so here we call relax P. If we solve P, is it equivalent to solve your original one? This will be very natural question. Very natural question. Yeah, because this problem is so nice. And this problem definitely can be connected to many difficult problems. Are those two problems equivalent? If you solve this one, do you solve that one? In fact, so we go through some very easy observations. So one observation, if you just take away the regularization term, so which means if you just take away this term, so here we regularize the boundaries by the length. If you just take away this one, consider the rest. Consider the rest. And then you are minimizing this one, 0, 1. So here is the sum of this one satisfy this constant. But you see that x point, this is every point are uncorrelated to each other. You can just simply take the omega away. If you minimize this on each point, and then the integral will be minimized. Because each point are uncorrelated. So you can just take this omega away. You minimize this one on each point. You minimize this one on each point. This is a linear minimization. It's a linear programming problem. Linear programming. And so one of the minimizer of a linear function over a convex set must be on the boundary of the constraint set. This for linear programming, this is always correct. If you want to minimize this one of the minimizer must be on the boundary. Thus, one of the minimizers satisfy this one. Especially if you use this figure, it's very easy to see. For this figure, you see, we just put F inner product with U. F is known. So U satisfies U1 plus U2 equal to 1. Each Ui is bigger than 0. And then you see this is essentially my constraint set. So here is a U1, here is a U2. U1 plus U2 equal to 1 in this line. You see that each Ui should be 0, 1, and that exactly gives this segment. That exactly gives segment. So F inner product with this U, and so therefore you see if F is pointing to this one, and this node must be the minimizer. If F is pointing here, and this point must be minimizer. If F is always parallel to this one, then every point on the line is a minimizer, include the two endpoints. So this means if you minimize on the whole line, the minimizer must be one of the two endpoints must be a minimizer. So therefore you see you relax, in fact the minimizer is still at one of those 2 points. And so this is very nice observation, and this is a key point. This is a key point. So there is some mathematical beauty here. You relax, after the relax, so the minimizer should be still one of the points. And this is something very beautiful. And here is, if you want to segment into 3 phases, and then U1, U2, U3 sum equal to 1 each sum. And this in 3 phases here is a U1, U2, U3, and then this is a triangle. And this relaxed one is a triangle. So the non-relaxed one is just one of those 3 points. So this the non-relaxed one is one of those 3 points. Again, if you minimize such a linear programming, it depends on F. So if F is pointing to this direction, this will be minimizer. F to here will be minimizer. Still one of those 3 vertices is a minimizer. So therefore, if you relax, your minimizer still is in your original. It is still one of those 3. So those 3 vertices as a non-relaxed. And this triangle is relaxed. So you can see that if you minimize in the triangle, the minimizer must be one of the vertices. So this is something very, very beautiful. And so that's the essential point. And so this means that here, the global minimizer with UI is equal to the global minimizer of the relaxed one. So those 2 problems are equivalent. And this is something very, very beautiful. But here we take away the TV term, we take away the length term. And the whole thing that if you add on the length term, this is still correct. But only if you add the length term, because TV is some kind of affine mapping. If you don't add the length term, if you add something else, you see like if you add the square or something beta, and then it doesn't work. But if you add the TV, and then everything still works. I'm not sure, do you catch my point? Yeah. So this, we talk about level set, and then we talk about labels, and then we talk about characteristics. So the characteristics, originally you need to constraint your U to be one of those three vertices, but we relax it, and then we constraint on this triangle. And due to this linear nature of the of the post model, you see that you minimize over the triangle, the minimizer still should be one of those three vertices. And so therefore you see they are equivalent. They are equivalent. This is something very, very beautiful. They are equivalent. So now we put on the TV term. So if we take this one away, we can see the relax and non-relax are the same. But now we put on this TV term. And then you see that we define this triangle by, this triangle even has a name, I think called the Gibbs triangle or something. It's a so-called, in 3D it's a triangle. When you have a morphosis, it's an abstract triangle. So we define these ones here. So here sum equal to 1, so here UI bigger than 0, because the sum equal to 1, so must be less than 0. So this exactly represents the triangle. So here we minimize, and this U should belong to the triangle. That's exactly the minimization we have derived maybe 2 pages ago. Yeah. So you minimize this one, you ask to be the triangle, and this is a term, and this is relaxed post model. This is relaxed post model.
May I see that?
Mm-hmm.
I'm sorry, because I'm not sure.
Right.
One question is, UI is depend on Fi.
UI, no. UI is a
The function UI is dependent on Fi.
No, Fi is a given.
Yeah, the component of F.
Fi is a given.
Yeah.
UI is a characteristic function.
So, but something looks like depend on Fi.
UI depends on Fi.
In this equation, looks like.
Surely the minimizer will depends on Fi.
Yeah.
The minimizer definitely depends on Fi.
So why? So this is there is any reason to put, because usual approach you try to segment the images.
Yeah.
So in the different way of level set. So
Yeah.
you try to these kind of things. But
Yeah.
so but in this approach usually we take the whole the image set like the normal F1 like that, but
So the Fi, so essentially, so let's use a region based. So you want to segment this U into n regions. Each region, you see, U should be and this one over each region, you should be U0 should be close to one constant Ci in omega I. So therefore, you see that assuming Ci is already known, I take Fi to be U0 minus Ci square. So this is my Fi. This is my Fi. So assume Ci is known, this is my Fi, and then I minimize this problem to get the omega i's. And then once I get the omega i's, and then I can average the U0, get the new Ci, and do another minimization.
sorry. Now I understand.
No, yeah, okay, very good. Yeah. So I'm happy if you ask questions. Right. Otherwise, if it's just a small thing gets stuck, maybe destroy your whole understanding.
I think my confusion comes from that fact. So we used to, when we say the segmentation, we mean that the segment divide the domain,
Yeah.
not the function, the domain of the image.
Yeah.
So this is what I am confused.
Yeah, so this Fi is equal to that one.
Yeah.
So this is once you get the Ci, you use this one to get the omega I. Once you get omega, you get new Ci, and you come back to here to again, and this is you segment the image. And so this Ui should belong to here. Now I'm just trying to show that if you put on the TV term, it still works. Because the TV, I don't know how many people of you are familiar with the TV. So the TV we talked about in the first lecture. So the total variation of a function can be defined as a U divergence. So this is a vector such that this vector is always less than 1. This vector is 0 on the boundary. And here, because we have a lambda, so we absorb this lambda to here. So this equal to P belong to here, U divergence P. This P is a vector, P1, P2. So that means you see that, so here is P1 x squared plus P2 x squared should be less than 1. Because of lambda, we put the lambda. So the TV term equal to U divergence P. P should be from here, and here you should maximize. Here you should maximize. And this is one special property of the TV. And so therefore, if you put this term into the previous model, so U will be from this Gibbs triangle, and this P, here is just P from C omega, so here UIF, and then here divergence P. Or here you get divergence PI. Because originally you have a UI here. So here you get divergence PI. So the original pulse model can again be written in this way. You get the U, you get the P, and here you get divergence P. And now you can see that if a P is known, you see this term is again like a linear programming. And this is the reason you see if you have a TV, the whole thing still works. Because if a P is known, this is like a linear programming for U. So this is the reason why if you have a TV term, it still works. But if you don't have a TV, if you have something else, so here, I don't know, you can put some other norms. Especially if you put the square here, definitely doesn't work. But for this case, U is a 0, 1, you see the square even not defined. But I'm just trying to show that only TV works. That's due to you have such a linear property. And this shows that if you put on the TV irregular length, and then the relaxed model still is equivalent to the non-relaxed model, this is still correct. And this is something mathematically very beautiful. Yeah. So let's continue. So if we do min-max switch, originally you min this one mark, we do min-max switch. Here Pi is corresponding to Ui. You do min-max switch, and then you get this one. And then again, you see here, so min-max switch, you first fix P, you minimize the U. This minimize U, this does not depend on, it's a linear programming. In fact, you have an explicit formula if you minimize this one with UI. So therefore, it's you see, once you write it down, you can see that you have a very explicit formula for that term. So essentially, you see like F1 plus divergence P1. You get F2 plus divergence P2. You have Fn plus divergence Pn. And then you multiply with this one by U1, U2, Un. However, you see that this one must sum equal to 1, and each one should be bigger than 0. If you do this one, you see that assuming this one is the smallest, you have n numbers here. Assuming this is smallest, you minimize with this UI. The minimizer is unique. You must put U1 equal to 1 here, everything else is 0, right? Correct? So therefore, if one of them is smallest, you minimize with this one. And then you see where the smallest, you must put that U as 1, the rest as a 0. So therefore, you see here you have an explicit formula. So the UI, that UI, which one, this is smallest, that UI must equal to 1, the rest must equal to 0. So this one equal to smallest, yeah. That one equal to the, you see, yeah, here I'm writing, you see here, equal to the smallest of this one. So therefore, so P marks, you get marks here. You see here is mean. It's just mean of those, and then you see that the UI disappear, and then you only have the PI which are left, which are PI left. PI left. So in this way, the characteristic completely disappear, and this is PI is a corresponding the corresponding vectors satisfy this PI equal to PI1, PI2, and then PI1 plus PI2 square should be less than 1 every point. So this will become the PI. Right. And so therefore we have one theorem that the PI to be optimal to the dual model, so which is the previous one. For each x in omega I, a binary primo optimal variable use can be recovered by this way. You see that. So here, assuming PI is the minimizer, if this one is, if the case one is the smallest, I just set UK equal to 1. Everything else is equal to 0. So that point you have a unique label. That point must be labeled K. Another point, if the tens label has the smallest, that point must be labeled 10. So essentially it depends on which one is the smallest. I determine a unique label you should have. There is a unique label you should have. And this is the way how do we determine the labels. And so therefore, if one of them is smallest, moreover, you can prove that this one must be the global minimizer for the original problem. It's a global minimizer. This is a binary. It must be 0, 1. It must be global minimizer of the original problem. So therefore, yeah. So this is another way to solve the problem. Maybe let's take a 15 minutes break. Yeah. Mm-hmm.